Cell arrangement. In this video, we'll be covering e-bike battery cell arrangements and calculating pack capability. Why it matters? Because it's fundamental to understanding e-bike battery packs, calculating e-bike range, and safe part selection. Prerequisite VODs, the one on voltage, current, and resistance, watts, amp hours, and watt hours, electrical circuits, and battery cells. Key terms. Number in series. So N in brackets refers to a number, and then S refers to series. It's the number of cells arranged in a series group. Example, 10S would be 10 cells in series. NP, same thing but for cells arranged in a parallel group. Example, 4P. Here's what that looks like visually. Many cells make an e-bike battery. Cells are arranged in series and parallel, as designated by what we just covered, S and P. Example, 10S, 6P. Or what we have here, 1S, because there's just one cell group in series, and 3P, 1S, 3P. Or here, 3S, 1P, because there's 3 cells in series, but only one parallel group for each series. When you add more cells in parallel, you add capacity. For example, say if you have 3 cells that are 3,500 milliamp hours each, you multiply that by 3 to get 10,500 milliamp hours, or 10.5 amp hours. You add their output, so if they're capable of doing 10 amps each, you multiply that by 3 to get 30 amps. And you divide the sum of the total internal resistance. So not all cells are exactly the same with the internal resistance, they can be slightly different, but for this example, we're going to say that they're all 15 milliohms each. Divide that by 3, that'll give you 5 milliohms. And in our example, if you were to change this parallel group from 1S 3P to a 1S 4P, that's where the cell would go. Note, when you add cells in parallel, all voltages will equalize with each other. So you want to aim for less than a difference of 0.1 volts between each cell when you add them in parallel, especially if you're building very large packs, because the higher energy cells will dump their voltage into the lower energy cells very quickly to bring everything to a balance. The lower the parallel group resistance, the faster the equalization. In parallel groups, make sure the polarity, the plus and minus side, are always aligned. So this is what a correct 1s3p should look like, and if you put one of them in backwards, you will get a short circuit, and at best the cell banks will drain and at worst catch fire. When you add more cells in series, you add voltage. Example, 3.6 volts times 3 is 10.8 volts. You also add the internal resistance. So if we had 15 milliohms and you times that by 3, you'll get 45 milliohms. Here's an example of what that series group looks like. And if you were to add an extra cell in series, that's where the cell would go in the dashed box. And when you're adding more cells in series, make sure the polarity flows one way. So again, align the plus and negative of each cell. This is what it looks like when you do it correctly. But if you put one of them in backwards, it's not going to be as dramatic as a short circuit in a parallel group. However, what you have is essentially one cell fighting all of the rest, and it will eventually break down and the cell or cell group will fail. E-bike battery packs typically combine both to achieve the required voltage, power, and range. Below is an example of a 10S 4P pack. So we have 4 in parallel, and we multiply that by 10 series groups. So let's do a little test on what we've learned. Let's solve for the pack's total voltage, amp hours, watt hours, internal resistance, nominal discharge and charge rate in amps, and lifespan. Now, in the real world, you normally only do one of these calculations, watt hours, but it is useful to know all of this stuff if you ever get into building battery packs. The example cell we have, which looks like this, is a lithium-ion 3.6 volt cell. That's its nominal voltage at 3,500 milliamp hours with 15 milliohms of resistance, a 5C peak discharge rating for 10 seconds, a 3C continuous discharge rate, and a max charge rate of 1C. The cell is rated for 500 cycles to a 80% state of health. So let's begin the math. I'll guide you through it and we'll look at the answers on the next slide. Beginning with voltage. 3.6 volts per cell nominal voltage times the number of cell groups in series, which is 10. Then we have amp hours, which is 3,500 milliamp hours per cell, and you times that by the number of cells in parallel. And then watt hours, we take the pack voltage times it by the pack capacity in amp hours, and that gives our result in watt hours. So here's the answers. 3.6 times 10 is 36 volts. Capacity times 4 is 14 amp hours. The watt hours is therefore 36 times 14, or 504 watt hours. This calculation here is the one that you'll be using most of the time, especially when comparing different batteries from different bikes. Next up, we've got internal resistance. So 15 milliohms per cell. We divide that into 4, and then we times that by 10. A thing to note here is the wiring is actually part of the complete battery pack. So technically that would become the internal resistance of the battery pack itself. However, that can change depending on the pack assembly methods you use, but for this example, it's a little complex, so we're just going to leave that one out. The answer is 37.5 milliohms. So that is 15 milliohms. Divide that into 4, which is 3.75, times that by 10, 37.5. Charge and discharge limits. So we know on our cell the peak rated discharge is 5C, the continuous rated discharge is 3C, and the continuous charge is 1C. So let's work that out together. The peak 10-second discharge is the cell capacity times its C rating, and then times by the number of cells in parallel. Same for the continuous and the charge rating. So when we break that down, it's 3,500 milliamp hours, or 3.5 amp hours, times 5, and then times that by 4, and that gives our answer of 70. Continuous is 42, and the max charge rating is 14. But what if we wanted to find out what these values were in watts? Remember, we're using lithium-ion chemistry, so we go off the nominal voltage. For watts, we simply take the cell nominal voltage, times it by the number of cells in series, and then times that by our limits in amps, which gives us 2,520 watts for the peak nominal 10 second, continuous of 1,512 watts, and a charge max of 588 watts. Now, that doesn't mean this pack needs to be at those values all the time, it's just the maximum rated capabilities of the cells in the pack. Lifespan or state of health, just like we covered in the battery cell video, pack lifespan is the same as cell lifespan. In our example here, each cell is rated for 500 cycles to 80% state of health. But in reality, cells all degrade at different rates, even if they're in the same parallel group. This makes it very difficult for an accurate calculation for a pack's lifespan. Sometimes you just have to go off the rated estimates. But if you have a customer that's asking, how much range do I get out of this battery? Well, there's a simple way to do that, and we'll cover that in later slides. So going back to that original problem to solve for all of the battery specs, we have everything here in a nice table. And we're just going to quickly look at another example, but we're just going to do one calculation set this time. So this is a 13S5P pack. So the voltage of the pack is 3.6 times 13 groups instead of 10. And the amp hours, it's 3,500 milliamp hours, or 3.5 amp hours per cell, times 1, 2, 3, 4, 5 in a parallel group. And our watt hours will be pack voltage times amp hours. Now, if you haven't been working along already, I want you to see if you can solve those. So pause the video here and then we'll skip to the answers. So our pack is a 48 volt pack. It is 17.5 amp hours, therefore 840 watt hours. And if you're curious, I did all of the math off screen just to give you a full fleshed out example of what the two packs are like side by side. But you might be wondering, Dave, what about customer FAQ? You know, range, lifespan, charge time? Don't worry, that stuff is coming. There's just a couple more factors to cover off about batteries that influence all of these things, and then having that knowledge, we'll be able to accurately answer those FAQs. Click here to watch the next video. It is the best free thing you can do to tell YouTube to support the channel. Otherwise, if you want to do more, check out the links in the description. Thanks for watching.